Well, hey, good morning, everybody. Um, uh, I was excited to. This is my first chance to get to speak at the guest speaker series, and I really appreciate the opportunity. Like Andy had mentioned, I'm a little bit of a stats guy. Probably not a little bit. For those who know me, I really like stats. You can go down some rabbit holes that aren't necessarily bad with stats, but sometimes it can be a little time consuming. But this is one stat that I felt was really worth the airtime and spending a little extra time on. So for those who aren't aware, our office went the entire calendar year last year with not a single tornado reported in our forecast area. So, right in the middle of Tornado Alley in the heart of the plains there. Pretty impressive stat. I feel like, if this had happened, let's say 20, 30 years ago, maybe it wouldn't have been, it still would have been impressive. But, with the advent of social media, a ever increasing chaser community, it, you know, it just seems really hard to believe, even as I'm saying this, it still is hard to believe that we went the entire year without a tornado. I also kind of like to find the silver lining in things, and I know 2020 had some difficult moments for many of us, and some of us are still dealing with some of that. But this was a kind of a silver lining um, from last year. So let's jump right in here. So how long has it been? Well, the last tornado in our forecast area was back in September of 2019, so a little over 500 days ago. Pretty incredible. That number is updated as of today. What's interesting is, so back in the fall of 2020, we broke our record for the longest period into a calendar year without having a tornado, and we've been breaking that record ever since. At some point, the record. I mean, I suppose it can't hold forever, being that it is Kansas. But for now, we just we keep each day we keep breaking the record. So, pretty remarkable stat there. Now for today's presentation, I was mainly just focusing on looking at tornadoes in general, but I thought it'd be interesting to look back at the last EF3 or greater tornado in our forecast area. And that one, you have to go way back, almost 1,000 days. So some of you might recognize that date, June 26, 2018. That was the Eureka EF3 tornado, which was not a classic tornado setup, more of your kind of maybe typical summertime setup, high cape, moderate shear, boundaries all over the place. And that was what led to that event, which was really just we had a couple of land spouts, but then we had the one EF3. Interesting, a little anecdote or side note there. I started here in Wichita in 2018 that summer, and that event actually happened about 2 weeks, I think, after I'd started. It was kind of a welcome to the plains moment. I'm excited and thrilled to be here on the plains, but it was funny because you start in a new office and you're still getting spun up. And I remember one point, we weren't sure if the cap was going to break that day. We had early morning convection that we were a little more overturned, but at some point we recovered really nicely by late afternoon, and boom, the cap broke on that day. And I remember the lead forecaster at one point, he was like, "Roger, I need you to put out a graphic," and I was like, "Don't know how to do that." So I was kind of scrambling and throwing together something, and we ended up getting some stuff out. And probably a couple hours after that, I remember taking a call from the emergency manager there saying, "Hey, we have a tornado on the ground doing damage." So anyways, it's interesting and pretty much that's kind of the biggest tornado event, quote unquote, if you will, since I've been here. So okay, so let's jump right in, kind of unpack this a little bit. Like I said, I like stats, so I like to give. I think stats are really neat, but then it's important to give a little context. So I wanted to give a little context on the kind of the anomaly of how quiet it was for our area, kind of put it in some regional and national perspective, and then we'll kind of dig into a little bit on some reasons why this happened. Okay, so first of all, we'll start here with number of tornado reports. Now, the note here on the map before I put it up is this is LSR counts. Um, so obviously, depending on how your office handles LSRs, you may get several reports of a tornado, and you LSR those, and then it ends up just being one tornado. So keep that in mind. But there's your map, and right there in the heart of the plains, in the heart of Tornado Alley, is a big gaping hole, which is our office. And some of the offices around us had some lower counts as well, so it wasn't just our office dealing with a quieter year tornado-wise. And again, the note there about the LSRs, Action Jackson, they're in central Mississippi. They were active last year, but they didn't have 140 tornadoes. So again, that's just looking at LSR count. Throughout the year, especially in the spring, our office started posting this map, and we would do an updated map every couple of months or something, and this got a lot of play just because again the novelty of it is the big hole there in the middle of the plains as far as tornadoes go. Okay, so I wanted to dive in then to just looking at actual tornadoes. So of course the others LSRs. And this is from storm data, the map. So this is looking at the entire year 2020, all the tornadoes. Of course you had your big hot spot there in the southern U.S. from Texas to Florida. You had some hot spots up north, the northern plains, and then up along the east coast there. But right there in the middle of the plains was Kansas. And again, it wasn't just our office. I mean, our office happened to be the one office that didn't have any tornadoes. But for most of Kansas, there's a lot of yellow space, at least on this map there. A little bit of a cluster over the high plains. I'm going to turn on my pointer here real quick. Yeah, so you had a little bit of a cluster here, but in some of the, pretty active for parts of the Ozarks and the southern U.S. That kind of caught a little bit of southeast Kansas there, but again, most of the state as a whole was pretty quiet. So another neat little stat thing here. I thought it'd be kind of neat to see which offices, and again, this is kind of come from storm data, but which offices had more tornadoes than us, and these would be offices that I wouldn't typically expect to have more than us, and maybe others would fall in that boat as well. So the NWS Albany office tops the list there with 14. Of course, the note is, obviously we all know the tropical season was exceptionally active in 2020. So there's, I think, a lot of these higher numbers along the East Coast are driven by the extra the higher than normal tropical activity. So I guess there's a caveat there, but still impressive nonetheless. So we'll keep going down the list here: Philadelphia, Portland, New York City, Glasgow, Montana, Buffalo, Boston, the other Portland. I thought that was kind of a neat. Both Portland offices, Maine and Oregon, had more than us. It still strikes me interesting that Portland, Maine had more tornadoes than us. That's a key takeaway for today. Kind of interesting stat there. And just, again, several of the New England offices. And we'll close out the list here with Seattle, Vegas, and Phoenix, all topping our office for tornadoes. One last way you can kind of look at it, just another map here, looking at tornado warnings. I like this map because the hot spots, of course, obviously a warning doesn't guarantee that you actually had a tornado, but it kind of shows the hot spots of the country. So you've got obviously your southeast, lower Mississippi Valley hotspot. Had another kind of interesting hotspot up here in the northern plains, and then of course your east coast, some of the tropical activity there. But we actually did have a couple of tornado warnings in our office. We matched the number of tornado warnings for Hawaii. I'm not aware of any of the climatology of tornadoes in Hawaii, but we had the same number as them. Okay, so now let's zoom in here. Just a couple more little on the stats side, and then we'll jump into the why. I wanted to focus on Kansas specifically, looking at the number of tornado watches. A couple of quick notes before I keep going. A lot of the maps that I've been showing are from the IEM data plotter, which if you've never played around with that site, it's a great site. Caution, you will get lost for days and days in there. So you can go down some not bad, but it will take you down some rabbit trails of there's so much data there to tell stories, and um, from climate to products. There's just it's a really good resource if you've not checked that out. So um, I'll have my contact info at the end, and if you've never used the site and want some more information about it, I can let you know. Or if you know of the site and just want to know how I made some of the maps, just I'd love to be able to help out. Um, so here we're going to show. All right, so this is again, we're just zooming in just on Kansas. So this is the average tornado watch count. And one note about the IM here is some of the data sets have limited windows, which is, so this one in particular only went back to 2005. So a little bit of a smaller sample size, but gives you about 15, 16 years or so there of Climo. So anyway, so looking at the, so, on average here in Kansas, we average about 2 to 5 tornadoes per year. You can see, interestingly, across southern Kansas is, if you're looking at the state as a whole, there's kind of a hot spot across southern Kansas, which for us, for our office, we actually, most of this hot spot area that where these higher on Climo, how higher Climo is, actually covers most of our forecast area. So it kind of speaks even more to the anomaly, the area with that's kind of the hot spot for Kansas for tornado watches, at least, was one of the quietest areas in the state. So this is kind of neat. So this is average, and then we're going to switch here to 2020. A lot of white space there. This transition is kind of neat. So for those, so bear with me. I'll do that one more time. Hopefully it shows up well on your end. But there's Climo and 2020. So a couple of watches up north, and then our southeast Kansas got caught with a couple there, but very quiet, very low. One of the things about this presentation too, on a side note, I had we'd been throughout the year last year, especially as we got kind of later into the summer and the fall. We were the conversation in our office about trying to figure out why this happened and the anomalies. We had a lot of internal conversations, but I feel like it's good to try to get some outside perspective when you can. So as part of putting this together, I reached out to SPC just to get their take. A lot of us are looking at convection for large sections of the year, but then we have some quiet times of the year, especially in the cool season. Whereas SPC, they're looking at that on a regular basis. So I just wanted to kind of get their take. So Rich Thompson graciously spent some time and looked through some of our notes and charts and just some things. So he was actually the one that had mentioned that the tornado watches were really lower than normal, and that really stuck out to him. So again, I appreciate his insight, and we'll hear a little bit more or a couple of notes from him later. Okay, so one last thing to look at stat-wise, convective outlooks, just another way to kind of give a flavor of how quiet or busy a particular month or time period was. Okay, so we'll start with May of last year. So this is looking at the highest day one convective outlook from SPC for any day, and this is just for our forecast area. So a lot of days in there with white, a lot of, so no outlook at all outside of just a general thunder outlook. Now, some of you maybe depending on where you're at, some of you may be thinking like, wow, that's actually, man, that could be a busy month for us, which true. There's some, for those who know this area well, there's, it can be quite a bit busier. So a little bit of relativity there. So interesting, we'll jump back here in just a second and look at May of 2019. So spring of 2019 was incredibly active for us. Not so much for tornadoes. We did have a few, but very active for severe weather and flooding. So let's just for comparison's sake take a look at what an active May can look like here in central and southern Kansas. All right, so there's May of 2019. So notice we ended the month there with 10 straight days of slight risk or higher, several enhanced risks, including a moderate. Again, for comparison, May of 2020, we ended the month with looks like 6 straight days without any outlook at all. And again, comparing that to 2019, very, very active year. When you spend when you're dealing with severe weather 10 straight days in a row, it gets a little sporty. So, anyways, just a comparison there of how busy it can be. Okay, so now the big question is, why did this happen? I think some of this is intuitive, and maybe it probably doesn't come without a surprise. I think it's interesting that some of the factors that we might look at on a weekly basis for what may be detrimental to severe weather or tornadoes. It's just interesting that we had these factors occur over and over throughout the spring and summer months. So we'll kind of unpack that a little bit. And quick note: any reference to spring here is March, April, May, unless otherwise noted. Now everyone's has their own forecast process. Mine, I tend to, especially during the convective season, I like to kind of do a top-down approach. Kind of, let's start with the large scale, upper level pattern. What story is that telling us? Chris, who will come here after me, he likes to talk about the story and what story does the data show us, or the models, or different things like that. So I really like his analogy there. So we'll try to see what this put all the pieces of the story together and see what we come up with. So here's looking at the 500 height anomalies from the spring, and for some of these anomaly maps here, I did March through June, just on a side note there. But key takeaway here is the trough axis, the mean trough axis, was a little bit further west than we'd like to see here, at least as far as for tornado potential. Typically you want something a little more, from Montana down through the central and southern Rockies, because that would put us in that good southwest flow, and especially if your trough can just kind of hang out there. You don't have, these big bowling ball lows or whatever that are just kind of moving bodily out and with tons of forcing. So you get more of these, waves coming out of the southwest, glancing blows. And the other thing too, it gives you kind of a good broad area of mid-level height fall, so that favors and encourages least cyclogenesis. And then of course, then you can, the big takeaway too is you can pull moisture in and then keep it here. So this year, plus, if I don't know about you, but if you're looking over the next 7 days and you're trying to pick out a day that you think might have severe weather or just convection, period, you're probably not, if you see a day where you've got a big ridge over the plains, that's probably not something you're going to be messaging convection much, or even severe weather potential. So again, above average heights and ridging favored during the spring months. So the other part of that then, and kind of the next piece of the puzzle, is with anomalous ridging favored, you also had anomalous mid-level temps. So you had a pretty impressive area there from Texas up to the central high plains of above to well above normal mid-level temps. If memory serves me correctly, I think we had even early in the spring, March and April, some warm temps over the Rockies and high plains. So you think each day you're with the EML plume spreading out over the plains, you're going to have some really warm air, which can be great for lapse rates, but at the same time, again, warm EML plumes. So you kind of infer from that maybe a stronger than normal cap. I was trying to think of the best way. There's probably some better ways out there to show how the cap strength compared to normal, but I was kind of using this as a proxy for again, kind of inferring that for a large part of the central and southern plains, you probably had a stronger than normal cap, which as we all know, that doesn't guarantee a lack of severe weather, but the stronger the cap, you're going to need a little bit more to overcome that. And of course, if you're dealing with somewhat persistent ridging, you're probably not dealing with very deep systems. So a lot of those things, those two pieces come together, which can be problematic. Chris, actually, in our office, he really likes to look at 700 temps for convection, especially MCS activity, but just convection in general. So when you're getting those warm mid-level temps, it can certainly be a problem. Okay, we'll step back up real quick to 500. So we looked at the height anomalies, and then here we'll kind of focus on just the mean heights. The reason I wanted to show this was kind of just as a way to kind of, again, a loose proxy for a way you can infer the mean, mid, and upper jet. So the main takeaway here is, again, there's some of your troughing out there on the west coast. You can see a little bit of a ridging there over the plains. Now, interestingly, on maybe some of the northern plains could chime in later or email me or something. But the biggest part of the anomalous ridge there focused more of the central and southern plains, but it's interesting that you had a little bit less ridging, mean ridging at least, over the northern plains. So perhaps that helped. We remember some of the maps showing a little bit of enhanced tornado activity across the northern plains. But for here in the central plains, when you've got more of that zonal flow, now this can be great. Some of you may be looking at this, and if you're seeing zonal flow, you're like, oh man, that can actually be really good for severe weather, especially MCS activity, and especially in the summer. This can be a great great depending on if you like or don't like severe weather, but it can be a really good from a probabilistic standpoint. It can definitely be kind of up that ante for convection coming off the high plains, and then growing upscale as it moves east and into the plains, Midwest area, and then even on into the East Coast. But for the spring, again, if you're from a storm mode perspective, MCS, you can have a lot of activity there, but maybe not your best tornado kind of setup. One of the things that and then so the progressive flow, that was the other part of it too. So we'd get these waves that would come through, and so we actually did have some decent surface lows that developed over Colorado and that would push east. The problem is because our flow is so progressive throughout the spring and summer, or especially the spring months, you think you get a low out here in the high plains of Colorado, and you're able to pull that moisture up, but then because it's progressive, it moves on, and then you push that moisture south, and it seems like over and over and over we try to pull moisture up and it would get shunted south. We try to pull it up, and compare that to where if your trough was a little bit more digging there, you think of the short waves kind of rounding the base and coming out a little bit slower, glancing the area, and you're not in that scenario, you're not pushing the moisture too far south, and you can pull it back north pretty quick. So with westerly flow, it's just not great. Rich Thompson had some of the same ideas. From a probabilistic standpoint, it lowers your potential for least cyclogenesis. Of course, all that that feeds back into your lack of low level jets, lack of low level moisture. So all of those things are, again, this pattern isn't horrible for severe weather, but when you're trying to look at tornadoes specifically, it's not great for our area at least. Okay, so now we'll kind of go down to the surface here and kind of take the upper air pattern there and how that can apply to the surface. So this map is, I think I feel like there's a lot of the maps have some pretty telling moments, but this map is incredibly telling. If let's say you're doing a forecast, you're looking out over the next 7 to 10 days or so, you're looking at a meteogram or something, and you kind of get a flavor of, or you see something like this. Does it scream tornadoes, or are you kind of pausing there? Well, let's take a look. Okay, the main takeaway here, and this is Point Wichita. So, and by the way, this is showing the average wind speed and direction for every day of May of last year. But look at that, we spent almost the entire month of May with northerly surface winds, which for those who know this area, I mean, that is bad news bears for tornadoes, or for our WCM. He loves to see that. Northerly winds are his friend. But I mean, just and again, you can kind of envision the progressive nature of the pattern. So let's see, late April, early, looks like there's a little southerly barb in there. So you think, okay, you have one system that comes through, and then you have a few days of northerly flow. Then you have another system that'll come through, and then you go right back to northerly flow. But progressive pattern in the heart of our severe weather season, not great, especially when you're dealing with a progressive pattern that leads to persistent northerly flow in the wake of each wave coming through. Interestingly, remember back in the convective outlooks, we had ended the month of May with like 5 or 6 straight days not even being outlooked at all for severe weather. And look at that. We spent the last, what this is, 5 straight days of northerly winds. It's, for pulling in, not just for pulling in moisture, but keeping moisture, it's just not great. So for a little perspective, here, this map shows, and this goes all the way back to the 70s. So looking at the average dew point, so for the month of May here in Wichita, what's the average dew point that we can expect based on wind direction? So obviously, if you're wanting good moisture return, you really want that some sort of southerly component of the wind typically off the Gulf there. Oops, sorry about that. All right, so yeah, so looking at May of last year, so here in the bottom right, that is where we lived. We just camped out in that northerly flow. What's interesting about this too is if you look, oops, turn my pointer back on. So if you look here, it's interesting, like, so northerly flow in general, especially, north and northeast, you're holding in the 50s. But what's interesting is anytime you have kind of this northwest or northwest flow, that's actually, of all the wind directions, that's our worst in May for dew points. So your average is there, upper 40s. So if we look back here at the wind, look, we had northwest, northwest. So not only did we have northerly flow for much of the month of May, we also had several days with more of that northwest flow, which, if you get a little more of that northwest flow, you start getting a little more downslopey and can even enhance the drying a little bit. So again, this is where we lived for spring of last year. So again, that's not great for us. Now some areas, depending on the country, part of the country, and dew points near 50, that can actually be really good for severe weather. And when I lived in Montana, if we had dew points in the 50s, that was like, hey, game on for severe weather. But so again, there's some relativity there. So let's take a look then, just to see how that compares to Climo and compared to normal. So again, 60 degrees, with a southerly flow, that's kind of our 50 degrees, especially maybe in March, that starts getting our attention. But when you start getting April, May, June, dew points in the 60s or higher, that's really where we start getting concerned. So I wanted to take a look at, this is again Point Wichita, looking at the number of days with a dew point at or above 60 degrees during the spring months. So there's 2020. So not the lowest on record, but you have to go all the way back a little over 20 years to have a spring that was as dry as last year, at least dew point wise. So that kind of gives you a flavor for southern Kansas. And then compared to normal, again, looking at the average dew point from 2020 compared to the average for the spring months in general, again, below normal. So let's go up north now, up to Russell. For those not familiar with the area, Russell's located right along I-70, and that's our northwesternmost county in our forecast area. So wanted to kind of give an idea from south to north. Same thing, there's 2020, very low number of days at or above 60. And in Russell's case, actually, it was the lowest number of days in over 30 years. So you go all the way back to the 80s there. One of the other forecasters' office, he mentioned just when we were looking at the charts, that some interesting years stuck out to him. He had some active years in the 70s. I think actually the Wichita one showed as well, like 2012. That was kind of our last big tornado outbreak, at least here that affected our area. So there are some impressive years, early 90s that show up. But 2020 was not one of those years. Okay, so let's skip ahead here. And hopefully everybody's caught up now. But again, there's looking at Russell again compared to normal. So in Russell's case, this was the first spring to be below normal dew point wise in about 5 years or so. Okay, one other thing to look at is mixing ratio. There's a lot of different ways you can look at moisture, obviously, precipitated water, dew point. Mixing ratio is one that that really caught Rich Thompson's attention. So this is we're still here at Point Wichita, or I'm sorry, Point Russell. So one thing to note here, so we're looking at just compared to normal. This the bottom part of the charts, the most important part here. It was interesting. We started the year a little bit on the higher side for moisture, especially January and March. And I won't steal any of his thunder, but Chris has some interesting research and thoughts on when you have some anomalous moisture and how that can factor into tornado outbreaks. So I'm really excited about what he has to share. But given some of his research, when we saw this last year, we were thinking, oh man, this is could be setting the stage for a rough couple of months for our tornado season. But then we hit here highlight we hit April, May, June, and man, we just really tanked. And one of the things, one of the notes from Rich was, almost all of your big severe tornado days should be in the upper part of the distribution, especially for that area. So for us, about 12 to 13. But he said you mentioned the anomalies. Not only do you want to be close to normal, but above normal. And we just really fell off. I mean, you have mid-April, mid-May, mid-June, not only below normal, but well below normal. So 3 somewhat consecutive periods there. We started to trend back up in July, but by then we're kind of getting out of our more favorable pattern for tornadoes. So you put all that together, lack of moisture, and what do you get? Large area of lower than normal instability across the central and southern plains, especially focused over the southern plains, but kind of stretching up here into the central plains. It's interesting. Just from what I can recall from last year, because even though Texas had lower than normal instability, you've got this big pool of moisture just hanging out to your south. So I think even with the progressive flow, the moisture got pushed pretty far south as far as our area goes. But for areas like Oklahoma, Texas, even with the progressive flow, they were able to pull some of that moisture back north, and of course the lower Mississippi Valley and Tennessee Valley areas. Very active last year. So even with the lower than normal instability, again, doesn't guarantee a lack of severe weather, but all those, putting all those pieces together, it favored a lower year for us. Okay, one last thing I just wanted to show, and then I'll be done. But I kind of a final piece of the puzzle, talking about the kind of the favorable or unfavorable time of day. So this is looking at central Kansas, so Wichita specifically here. So in general, and this may not differ much from other places on the plains or other areas of the country, but in general, we kind of have two windows where we're looking at convective potential. We have the late afternoon, early evening period, and then kind of an overnight, early morning period. Sometimes they kind of roll into each other. So this is just looking over the last 30 years, kind of looking at your time frame there. Typically the middle of the day, noonish or so, is our kind of our low point for convective activity. But what's interesting is to compare that. Let's compare 2020 then with CLIMO. So the main takeaway here, and again, we're just kind of looking in the right, the right side of this chart. There's a lot of noise here, so don't let that scare you or anything. Excuse me. But the main takeaway here is, so first of all, so we compared to CLIMO, we had our overnight, early morning activity. What was interesting is one of our forecasters was looking back at our convective warnings last year, and for the month of May, about 70 to 80% of those warnings all fell in the midnight to 8 a.m. range, which for MCS activity that's not unheard of, but for the bulk of your warnings to be overnight, that stood out to us as pretty anomalous. So but putting all those pieces together, going back to that pattern that we had, kind of that west northwest flow, like I was saying, it makes sense that you'd still favor some overnight activity. So we basically kept our overnight period, right? But what about that late afternoon, early evening period? And look at that. I mean, we had some afternoon and evening convection, but we really, really lost our prime tornado window as far as time of day goes. So we kept the overnight early morning activity, but we really lost this afternoon, early evening period. And again, I think that speaks to, a number of things. We had some really strong, we had a number of events where we had a really strong cap in place. Of course, you might have some decent forcing with some of those, even with that progressive flow, you might have some decent forcing with some events. But if you're not able to pull that moisture north, I mean, it's just there's a lot of limiting factors for breaking the cap, just in general. And then if you put a stronger than normal cap in place, now you've got to work even harder. So it doesn't surprise me. It's telling, but yeah, we lost that afternoon, early evening period. So I was like, I'm a key takeaways guy. Just wrapping it up here. So ridging, so some things that just really, again, from a probabilistic standpoint, really were detrimental for us for not only tornadoes, but severe weather in general. Ridging with more mid-level temps, stronger cap, extended periods of northerly surface winds. Of course, that leads into lower than normal moisture and instability, and just a general overnight convection favored, and then less of that afternoon or early evening period. Okay, well, with that, I will go from bottom up just to be different, I suppose. But I thank you, Central Region, and Andy for hosting this and letting me chat a little bit today. I again appreciate Rich, his help, and just kind of QCing some of what we were looking at, and also Jim Caruso, our Sioux, for looking over. There are a lot of great Siouxs out there, and Jim is definitely one of them, and he's very supportive of some of the stuff that Chris and I have been working on in different projects and research, and so I really appreciate his help. And with that, I will toss it back to you, Andy.